CBSE Standard 12 CBSE Standard 12 previous year's questions answer for physics. Okay, and this particular chapter from which we are discussing questions answers are from electromagnetic inductions and alternating current. Okay, let's resume our discussion. First question: a group of students while coming from school noticed that a box danger HT 2200 volt. Okay, so this type of in the electrical power substation, this type of box with the danger mark we have seen, correct? So in a box it is written that high tension, HT means high tension, 2200 volt. Okay, this is the message written at the substation, electrical substation in the main street. Okay, they did not understand the utility of such high voltage, while they argued the supply was only 220 volt. Okay, because in our household near our residence we need actually 220 volt. So if it is written 2200 volt, whereas we need only 220 volt to operate our electric appliances, why it is like this? Okay, they asked their teacher this question next day. The teacher thought it is very important question and explained, okay, the whole class. So answer the following: what device is used to bring high voltage down to low voltage AC? Okay, what is this device? This is a transformer. So you know, from the power generation station, suppose this is the power generation station. Okay, from power generation station we supply through the transmission line. What we do, we supply high voltage current. Okay, voltage is very high but current is very low. Why it is high voltage? Because if current is more, then most of the energy will be wasted in the form of heat energy. That is from the power station. Okay, we actually step up this, and near our locality, near our residence, there is a step down transformer. So what it does, this transform 2200 volt to 220 volt. Okay, so input is our 2200 volt and the output is 220 volt, correct? So this type of thing where the voltage lowered down is called a step down transformer. So what is this device is used? This device is used as, this is called transformer. Okay, so high voltage down to low voltage is a step down transformer. The AC current, and what is the principle on which it is working? So we already know that transformer is based on the principle of mutual induction, correct? Where the AC source, the input that is 220 volt is connected across the primary, and the load across which we need the output. Okay, here this is the secondary. So from the primary we here 2200 volt will flow, whereas in the output the number of turns is made in such a way that at the output we get only 220 volt, correct? So the principle is very, very clear, that is, it is based on mutual principle of mutual induction. Okay, now is it possible to use this device for bringing down the high DC voltage to low DC voltage? Now see, since the transformer is working on the principle of mutual induction, and what is mutual induction? It is actually a phenomenon of electromagnetic induction. Okay, now for electromagnetic induction what we need? For electromagnetic induction we need that the magnetic lines of force should cut the plane of the coil, secondary coil, and this number of lines of force should vary with time. In case of AC, both the conditions are satisfied, means it is varying magnetic lines of force. It is changing with time as well as cutting the plane of the secondary coil. But if it is a DC voltage, what is DC voltage? It is smooth voltage. Okay, it is not changing with time, it is a fixed voltage, correct? So in DC voltage mutual induction will not happen, electromagnetic induction will not happen. So in transformer, if you want to transform voltage of DC, then it is not possible. Okay, explain. Because the magnetic lines of force are not varying, that is why we cannot use in DC. Write the values displayed by the students and the teacher. Okay, inquisitive mindset, okay, scientific temperament is there. So just take the screenshot of answer. I have explained it in detail. It is a step down transformer, and making it bigger so that you can take the screenshot. Okay, so this question is answered now. This question, take this part 2, 3. Now next question, define mutual inductance. Earlier we have defined mutual induction. Now this is the question of you have to define mutual inductance, and what is the SI unit of mutual inductance, correct? Derive expression for mutual inductance of two long coaxial solenoids. Okay, coaxial means their axes are same. This is, suppose this is one solenoid S1 and this is S2. This is S1. Okay, both the solenoid means a spiral coil. Okay, if there is nothing inside, then it is air core solenoid. If over iron bar spiral things is bounded, then it is called iron core solenoid, correct? So the axis of S2 and S1 is same, that is why it is coaxial solenoid. Okay, so same. So we have to derive the expression of mutual inductance. Now in an experiment, two coils C1 C2 are placed close to each other. Find out the expression for EMF induced in the coil C1 due to the change in current in coil C2. This is very, very important question, and most repeated question. This type of questions is asked repeatedly in this CBSE board 12 exams. Okay, so we will answer one by one. First of all, what is mutual inductance? So we know that the flux, the magnetic flux equal to is proportional to the current flowing, so it is equal to M into I. This M is called the coefficient of mutual inductance. Now if phi equal to M into I, now if we make I equal to 1, then phi equal to how much? Phi equal to M. So we can define that if unit current passed, the flux is equal to the mutual inductance, correct? So we have made I equal to 1 here, so then phi equal to M. Thus mutual inductance of two coils is equal to the magnetic flux phi linked with the one coil when the unit current pass through the other coil. This is one definition number 1. We can define mutual inductance in this way also. Okay, from Faraday's laws of electromagnetic induction, we find that E equal to minus M di by dt. Okay, so later we will explain what is phi, what is the significance of negative sign through Lenge's law. Okay, let us use this expression E equal to minus M di by dt to define mutual inductance, correct? Now here, if rate of change of current di by dt, suppose di by dt is rate of change of current. Okay, the current change taking place per second. If we make it 1, then what will happen? E equal to minus M, or in magnitude purpose E equal to M we can write, correct, for magnitude. So mutual inductance, this is second definition, is equal to the induced EMF set up in one coil when the rate of change of current flowing, means di by dt, through the other coil is unity, correct? So what is the unit? Unit is Weber per ampere. Okay, unit of mutual inductance. Okay, now we will explain this. Two coaxial solenoids are there, and we have to find the expression for mutual inductance. Okay, so suppose in the coil there are two solenoid. This is inner solenoid is S1, the outer solenoid is S2. Inner solenoid is having number of turns N1, the outer solenoid has number of turn N2. The inner radius of this inner solenoid is R1 and radius of the outer solenoid is R2, correct? This is R2. So we have defined this thing. Now, so So considering the figure, you have to draw this figure. Okay, this R2 means this is the outer solenoid radius. Two coaxial solenoids we have taken, and their lengths are taken as same. Okay, length of both the solenoids are same. Let the radius of the inner solenoid is R1 and number of turns of the inner solenoid is N1. Okay, the corresponding quantities for the outer means S2 solenoid is R2 means radius, N2 is number of turns, N1, N2 are the number of turns. So be the total number of turns in the inner and outer, correct? So when I2 current is set up through S2, the magnetic flux phi1 is set up in it. The flux is equal to how much? Flux is equal to number of turns. Flux is proportional to the rate of, so flux is equal to N1 into phi1 is equal to mutual inductance into the current. So this is for the first. Okay, now where M12 is what? This is the mutual inductance of the solenoid S1 with respect to the solenoid S2. So the magnetic field due to the current I2 in S2, okay, is mu0 into N2 into I2. In L length we have number of turns as N1, correct? So L, what is N1? Let us see again. L length, what will be the number of turns? N1 into L, correct? So N1 into is the total number of turns, that is capital N1. And what is phi1? Phi1 is equal to flux is equal to area pi R1 square into mu0 N2 into I2, correct? So it is mu0 N1 into pi R1 square, this is the area, into I2. So here N1L is the total number of turns in the solenoid S1, correct? Okay, so what is N1? Small n1 is number of turns per unit length, number of turns per unit length, correct? So N1 into L is the total number of turns. Similarly, okay, so this can also be written as, from this is equation 1, okay, and this is equation number 2, correct? From these two equation, both are N1 into phi1, correct? So we can equate these two, that the mutual inductance M12 into I2 is equal to this much. So this is what we need to find out, mutual inductance. Okay, now consider the reverse case, means I1 current is passed through the inner solenoid, okay, and the flux linkage with the outer solenoid S2 is N2 phi2, okay. If mutual inductance earlier case was M12, now we have written it as M21, correct? So M21 is what? This is the mutual inductance of the solenoid S2 with respect to S1. Flux due to the current I1 in S1 can be assumed to be confined solely inside S1. Since the solenoids are very small, the flux linkage with solenoid S2 is equal to similar case. N2 phi2 is this much. What is N2? N2 is number of turns per unit length. We have taken length same, so total number of turns will be number of turns per unit length into total length of the solenoid, okay. Now, so if we equate these two, then we find that M21 is equal to this. So from equation 3 and 4 we get that M12 and M21 equal to say M. So therefore M equal to, we can write it mu0 N1 into pi into R1 square into L. Okay, this is the mutual inductance expression. Okay, second part, considering, let us come to the second part. What is this? In an experiment of two coils C1, C2 placed close to each other, find out the expression for induced EMF in coil C1 due to the change in current through C2. Okay. Now this part. So first of all, you take the screenshot of it and remove this part. That's the complete answer for the first part. Take this screenshot before explaining C2. And remove this part also. So that you can take the, for writing in the examination hall, you need to write like this, okay? Take this screenshot. The complete answer of this question. Okay? So we have answered A and B. Okay? Now we are explaining answer of question number C. Considering a coil C2 where I2 is the current flowing and there is a coil C1 kept in front of C2, so that varying magnetic flux cut the plane of C1 and mutual induction takes place. Means what? There is a coil here. This is C2, okay, and there is a coil here. This is C1. So because of and the magnetic lines of force in this coil, here we have connected some AC source. So the magnetic lines of force cutting the plane of C1. Okay, it is varying in nature because it is AC, and it is cutting the plane of the coil C1. Okay, therefore the magnetic flux phi1 induced in C1 is proportional to the current which is flowing through this I2 coil C2. So phi1 is proportional to I2. So phi1 is equal to how much? If we want to replace this proportionality sign, we need a equal sign and a constant. This constant is mutual inductance. So phi1 is equal to M into I2, correct? Now d phi1 by dt equal to, differentiate both sides, is equal to M into di2 by dt, because M is constant. So only variable is current, it is AC current. So E equal to, so now the EMF induced is proportional to d phi by dt, correct? So EMF is equal to, and d phi by dt we have already find out, so minus M di2 by dt. Okay, this is the induced EMF. Now negative sign simply indicates that the direction of the current C1 is such it opposes the cause. I will explain this part now. Let us remove this. What is the meaning of this negative sign? Okay. Now see, because first coil, suppose the first coil current is flowing like this, correct? Or current, direction of current like this, okay? Now this is the direction of current in the coil C2. In our question, this is C2 coil. Now if we rotate our right hand along the direction of current, then the thumb gives the direction like this. Okay, this is supposed to be the north pole of this, and this is the south pole. Now what will be the direction of current here? Okay, this is explained by Lenge's law. So this is C1 coil. Now if north pole is there, now it will not create south pole here, it will create north pole here, so that it will oppose it. Now to create north pole here, okay, so the direction of our current should be such that if we rotate our right hand like this, okay, along the direction of current, then the thumb gives this direction, so north pole will be produced. So this produced EMF is such so as to oppose the very cause due to which it is produced. Means this EMF induced in the C1 is because of the varying magnetic lines of force from C2, and this side of C1 is faced by the north pole of C2, that is why north pole will be produced here, correct? So that is why the EMF is induced so as to oppose the very cause due to which it is produced. So that is why this negative sign, correct? It opposes the cause. Similarly, we could have produced current. I'll explain again this Lenge's law, because in your next questions Lenge's laws asked frequently. Suppose North Pole is approaching here, okay? So what will be the direction of current here? Here also, if we bring a North Pole towards this closed coil, then what will happen? The magnetic lines of force cutting the plane of this coil will change. Okay, flux is cutting this coil, so therefore the EMF will be induced. Now it will produce EMF in such a way that North Pole is produced here in this coil. So if we write N in this way, means direction of current will be like this, correct? Direction of current is like this. So then only North Pole will be produced. Similarly, if we bring a South Pole here, suppose South Pole towards a closed coil, then so the EMF induced in this coil should be such so as to oppose the South Pole. Now how the opposition will take place? If South Pole is produced, then only the opposition will take place. South Pole means write S. This is very easy to write down the direction of current. S means direction of current will be like this, just opposite, correct? So again I will explain this, but this is the negative meaning of this negative sign. Let us take the screenshot of it. Okay. Next question. An inductor L. Okay, this is inductance L. The inductance means the resistance of what is XL is connected in series with the bulb B and AC source. Okay, how would the brightness of the bulb change when the number of turn in the inductor is reduced? If the current is reduced, then how the bulb will be, whether the bulb will be brighter or dimmed. Okay. Now an iron rod is inserted in the inductor. Okay. Then what will happen to the brightness? A capacitor of resistance XL is equal to XC is inserted in the series in the circuit. Okay. Then justify answer in each case. So let us analyze this question and visualize this question, because this question carries half marks for each small part. Okay. So first of all, inductor is a spiral coil like solenoid. Okay, this is inductor, and it is connected with a AC source. There is a AC source that we have connected. Okay, so this is AC source, and a bulb is also connected. Okay, so let us write the bulb like this. Now let us let us see case 1 first. Okay, if the number of turns in the inductor is reduced. Okay, now what is the resistance offered by inductance? It is written as XL. XL is equal to omega into L. Okay, omega is the frequency of AC and L is the coefficient of self-induction. Correct? L is the constant of this coil. Now on which parameter L depends? L depends on the number of turn. Higher is the number of turn, higher will be the L. Now if the number of turn is reduced, then what will happen? L will reduce, because L is proportional to number of turns in the solenoid. More is the turn, more will be the value of L. Now if N is reduced, number of turn reduced, L will reduce. If L is reduced, L is decreased, then XL is what? The resistance offered by this inductance, means inductive reactance. The inductive reactance will decrease. Now if resistance is decreased, then what will happen? More current will flow, the bulb will grow brighter. If the resistance, so ultimately in one sentence, if we want to say that if the number of turn decreases, current in the circuit will increase. Correct? Because back EMF produced due to the self-induction will be more. Back EMF cancels the actual input voltage applied in this circuit. So if the number of turn decreased, the resistance offered by the solenoid will decrease. If the resistance in the circuit decreases, current will increase. If more current flows, then the bulb will be brighter, correct? So the current in the circuit increases, so brightness will increase, correct? First part is answered. So let us take the screenshot of it. We'll analyze the second case. So only our basic emphasis is you should understand what you are writing, then only you can attempt even in the competitive examination such type of questions, okay, where basic understanding is necessary. Now second part, here an iron rod is inserted. So see what happens between the air, this is when there was nothing, air was there inside this solenoid, this is called air core solenoid, air core, okay. Now if we insert an iron bar, then what will happen? The flux leakage will be less, because in iron core solenoid the flux leakage is more, because air, the permeability of air means degree of allowance given to the magnetic lines of force produced because of this varying current, okay, is less in air. But if iron is ferromagnetic material, okay, so the flux leakage will be less because the permeability of iron is more, correct? So this is exactly what is happening when you are inserting iron. Then what will happen? Inductance of the iron core is more than the air core, correct? Why inductance is more? Because iron is ferromagnetic material and carries more magnetic lines of force. It allows more magnetic lines of force to pass through, correct? So reactance will increase, because inductance increases, reactance will increase. So if the resistance offered in the circuit is increasing, then the current will decrease. If the current decreases, it will be dim. Bulb will not result that much brightness. So brightness will decrease. Correct? Second part is also answered. What happens when iron is inserted? Now, third part of this question. Let us do the third part. A capacitor of reactance XC is equal to XL means you have introduced, initially there was inductance, okay. Now, and this load means the bulb means our resistance, okay. This is in our electrical circuit, a bulb is a resistance, ohmic resistance it has, okay. Now we have introduced a capacitor. A capacitor is introduced here. So it is LCR circuit. Now AC is connected. So what will happen? And it is given that the resistance offered by the capacitor, this is called capacitive reactance, is same as the resistance offered by the inductance. Now in a capacitor, the current leads EMF by 90 degree, whereas in inductance current lags EMF by 90 degree. Correct. In other words, we can see in capacitor current lead the voltage lags across capacitor by 90 degree, and inductance the current lags means voltage leads by 90 degree, okay. So what is the total impedance when in a LCR circuit? So the total impedance offered in LCR circuit is equal to how much? R square plus XL square minus XC square, okay. That is root over R square. What is the resistance offered by inductance? Omega square L square minus 1 by omega square C square. Now since XL is equal to XC, because of phase difference between current and voltage, this reactance will cancel out, okay. The total impedance of the circuit, total resistance offered by combination of L and R will become 0, okay. If resistance offered is 0, what will happen? Current will increase. If current increases, then the bulb will glow brighter, correct. So see, inserted, then the Z equal to R, only the impedance, only the resistance offered is the ohmic resistance of this bulb. So and the effective impedance is total resistance. is minimum, so current will increase, the brightness of the bulb will increase, correct? Now next question, let's take this screenshot. Okay, we'll go to the next question. Write the expression in vector form for Lorentz magnetic force F due to the charge moving with a velocity v and magnetic field in magnetic field B. Okay, this is just the expression. It is half and half marks force, and half marks is for writing this expression, half marks for explaining the direction. Okay, so the Lorentz force is equal to charge into charge is scalar quantity, velocity cross the magnetic induction vector. This is equal to the force. This is Lorentz force, correct? So if we write the expression, a charged particle in motion is associated with a magnetic field because of its motion. Okay, static charge means electrostatic force, but a charge in motion creates magnetic field, and this will interact with the magnetic field of the existing vector B. So it will experience a force V cross B. V is velocity V. Now if we want to find out the direction, we know that how to find out the direction of the two cross product of vector. Now the force is perpendicular to both the plane of velocity and B, perpendicular to both this plane, correct? So direction is perpendicular to the plane containing velocity and V vector. So if you rotate our right hand as in the cross product happens, from the first vector to second vector, thumb gives the direction of force. So F is perpendicular to velocity and perpendicular to the magnetic induction vector of external field. So direction of force can also be obtained by applying the cross product. Okay, so this question is very simple. Okay. Next question. Out of two magnetic material, A has relative permeability slightly greater than unity. Okay, while B has less than unity. Okay, identify the nature of materials A and B. Will their susceptibilities be positive or negative? Okay, so see, we have three kinds of material. One is dia, other is para, other is ferro. Okay, so for dia the magnetic permeability is less. Okay, and what is relative permeability? It is absolute permeability by, writing the expression of permittivity, actually the symbol is permeability. So what is relative permeability? It is permeability of the medium to permeability of air or free space. Now for dia the relative permeability is less than 1. Okay, for para the relative permeability is nearly equal to 1, and for ferro the relative permeability is greater than 1, correct? So now we can distinguish that A is paramagnetic, okay, because it is given that the A has relative permeability slightly greater than unity. So greater than 1 unity means paramagnetic, and B is slightly less than unity, so B is diamagnetic, correct? Okay, now so this is the expression. Now also susceptibility of A is positive and susceptibility of B is negative. Now what is susceptibility? Okay, we'll explain, because here it is not asked what is susceptibility. Okay, that is a bar, suppose what is the meaning of susceptibility? I'll explain a bit. Suppose you have an external field on which a bar to be magnetized is kept. So when the external magnetic field, if you keep a iron bar here, suppose, okay, so what will happen? It develops magnetization, because it develops magnetization. So if it develops more magnetization even after removal of this external field, we say that it is more susceptible to retain that magnetization. Okay, the susceptibility will be more. This is the physical meaning of susceptibility. It is somewhere related to intensity of magnetization. So we will explain if we come across such questions. Okay, next question. State Ampere's circuitous law expressing in the integral form. So Ampere's circuitous law is very simple. The line integral of magnetic field over a closed loop is equal to the mu 0 times the current flowing, correct? Mu 0 times the total current flowing. So B0 is the magnetic field, length is dl, so over the entire loop, so it is the line integral, okay, it is B dot dl is equal to mu 0 times the current flowing, correct? So we apply this Ampere's circuitous law in various applications while solving numericals, correct? Now this first part is answered, very straightforward question, simply you have to write the statement. Now second part is two long coaxial coil S1 S2 inserted, similar to the previous, we have already explained this thing, okay. So here also inside on the axis, outside the axis, okay. So you have to find the magnitude and direction of net magnetic field at a point inside on the axis and outside the combined system, okay. Here last time we did a coaxial solenoids mutual inductance, but here we have to find out the magnetic field, okay. Let's do it again. Okay, so we have taken actually two coaxial solenoid, okay, S1 and S2. This is S1, inner one is S1, the outer solenoid is S2. The inner radius of the solenoid is R1, the outer radius of the solenoid is R2, and length of both the solenoids are taken same, correct? L is the length of each solenoid. So the magnetic field developed because of this, the magnetic field inside the solenoid on its axis, okay, we have, or there is a derivation for magnetic field because on the axis, because of the current flowing, is number of turns into I into mu 0, okay. So here straightforward we can write this is the magnetic field, and direction is what? If you grasp the solenoid along the direction of current, okay, suppose this is the current flowing, then the thumb gives the direction of magnetic field produced, okay. If current is flowing like this, then rotate your right hand along the direction of current across the solenoid, the thumb gives the direction which is along the axis, okay. So this will be the direction of magnetic field, okay. Now therefore B1, the magnetic field produced, is equal to mu 0 N1A. B2 means the magnetic field produced because of the N2 turn is equal to mu 0 N2 into I, correct? And assuming that N1 is more than N2, number of turns are varying here, okay. So the resultant magnetic field, okay, here it is given that the steady current I flows through the inner solenoid to the outer solenoid, which is connected to the outer solenoid, through which the same current I in opposite direction flowing, okay. So if the inner coil produces a magnetic field along this direction, the second coil, that is the outer coil, the direction of current is just reverse. So automatically what will happen, if direction of current is reversed, then it will produce a magnetic field in this direction. So the resultant magnetic field will be just, they are 180 degree apart, correct? B1, B2. So we can subtract these two to find out this. So B1 minus B2, here number of turn, we have assumed that N1 is greater than N2. Otherwise, if number of turns in the second is more than first, then N2 minus N1 we can write, okay. But the algebraic substitution of these two magnetic field will give us the resultant magnetic field. This is I am sure about it, okay. So here, as per this condition, the outside the combined system magnetic field will be 0, okay, because this number of turns, so outside the magnetic field means this will cancel each other, correct? Magnetic field, okay, and the direction of current is also reverse. So just take the screenshot so that you can reproduce it in our exam. removing this part. Okay. Now go to the next question. Describe simple experiment or activity to show that the polarity of EMF induced in a coil is always such that it tends to produce a current which opposes the change of magnetic flux that produces it. Okay. So suppose you let us take a closed coil here. Closed coil means, suppose here we have a galvanometer or ammeter to detect the current. Okay, and north pole you bring. If you bring a north pole, what will happen? The current, when we bring a north pole, what will happen? The magnetic lines of force cutting this plane of the coil, this is cutting, as well as if we have a speed of this magnet, if we bring with certain speed, then this will vary with time. Okay, so what will happen? EMF will be induced across this coil. So the direction of EMF is such that it will oppose the approaching north pole. So this is when this will happen, if north pole is produced here. Okay, because small current carrying coil is similar to a magnetic pole, so current will be along like this. Okay, this will be the direction of current. Similarly, if we recede the south pole, suppose we have a south pole, and if you want to, from the close proximity of this coil, if you recede this coil, if you take it away from this coil south pole, then this direction of this current will be such that it will not allow to leave this south pole. It will try to attract the south pole. In this case also, when the south pole is taken away from this coil, then also here north pole will be produced, because the EMF is such so as to vary cause due to which it is produced. So south pole is receding, so if north pole is produced, then only south pole can be attracted, so it will oppose this receding, so it will attract, correct? It will not allow to recede, it will not allow to taken it away. Now suppose south pole is approaching a closed coil. This is a closed coil. I have taken simply just for understanding one turn coil, and this is a galvanometer or ammeter to detect the current. Okay, direction of current. This is a south pole is approaching. Now the direction of current is such that it will repel the approaching south pole, correct? So how it is happen? If south pole is produced here, if south pole, if you want to produce south pole in the coil, then the current direction will be like this. Remember, just opposite when the north pole is producing. Then only south will repel, correct? Or if you recede, if you take away the north pole from the close proximity of this coil, if you take away, then also south pole will be produced, because the reason for induced EMF is north pole receding, so south only can attract this north pole. So in both cases, whether south approaches, north recedes, the direction of induced current and EMF is such that it will oppose the cause. Okay, so this is clear, this experiment. The current flowing through the inductor of self-inductance air is continuously increasing. Plot the graph showing variation of magnetic flux. Okay, now in inductance, if you increase the current, then what will be the inductance? Okay, so you have to plot the graph of magnetic flux versus current. This is a very good question. Induced EMF versus di by dt, rate of change of current. Magnetic potential energy stored versus the current. Very good question. All the concept will be clear for this. So first part we have already answered. If north approaches or south recedes, both case north pole will be developed, correct? Second part, if south approaches or north recedes, then only south pole will be developed. This part is clear. Okay, now come to this. Okay, now this is the direction of current, this is the magnetic flux. More is the current, more current flows through the inductance, more magnetic flux will be produced, correct? More magnetic flux will be produced. So if we plot a graph of I versus flux, then it is a proportional, means when no current is 0 at the origin, So a straight line will be obtained, correct? So E is d phi by dt. Now voltage versus, okay, now if di by dt versus EMF is plotted, so what is di by dt increases, induced EMF will also will increase, because the mode is the speed of the armature between the north and south pole. Okay, this is the basic principle of electromagnetic induction. Mode is the speed, mode will be di by dt, and higher will be the induced EMF, correct? So but the direction is just opposite, that is why induced EMF is taken along this. So they are also proportionality sign, but with a negative means direction is taken as negative. Now here, okay, so di by dt increases at a constant rate, the EMF becomes constant. If di, there is no variation, okay, at constant rate, then this will be smooth. Okay. Now third is, what is stored energy? And stored energy in inductance is this. This is actually asked in objective type question as well as for solving your basic standard 12 numerical problem. Okay, so the energy stored in solenoid is half L into I square. Now if we put I in along x-axis and stored energy along y-axis, then what will happen? If I increases, it is a quadratic equation, so it will not be a straight line, it will be just like curve. So this is the curve. Okay. Now I want to finish this electromagnetic induction chapter today, because we have to go a long way, okay, and your examination is nearby, so let's try to avoid repeat question. Now draw the schematic sketch of AC generator, okay, describing the basic elements. Okay, state briefly its working principle, show plot of variation, magnetic flux, alternating EMF versus time generated in the loop. This you should know. This is the AC generator. What is the basic principle? If you rotate a closed coil, okay, between the north-south pole, okay, so twice it will be parallel to the, if a 360 degree rotation of this coil will make 2 times the coil to appear parallel to this magnetic lines of force, correct? Because this is radial in nature, magnetic lines of force because of north will be radial in nature. So twice it will be parallel to the external magnetic field, correct? So twice it will be 0, and 2 times it will just be perpendicular to this magnetic lines of force. So 2 times in one cycle, in one AC cycle you have seen, no? 2 times it is maximum and 2 times it is 0. It is maximum here, correct? So this is slip rings, this is alternating EMF developed. We can take it out the load voltage here, and this is carbon brushes. This is the coil armature. It is actually represented by a single turn, but it consists of many turns. More is the turn, more will be the EMF index, means electromagnetic induction. This is the axis of this coil, correct? So this is a simple AC generator inside schematic diagram. The principle already I have explained, just you can read it out. Okay, and the magnetic flux linked with the coil is NBA cos omega t. Induced EMF is d phi by dt. If you differentiate it, then it is omega. So NAB omega sin omega t is the EMF. So what is this constant? When what is the peak value of EMF? When sin omega t is 1, correct? So when sin omega t is 90 degree, means it is 1, then what is EMF? EMF is equal to N B A omega, correct? So this is called the peak value. So we have represented by E0. So replace this part by E0. So now it is a very simple equation. E equal to E0 sin omega t. In some of the book it is written as EP sin omega t. Doesn't matter. It is the maximum value of EMF, correct? So this much is clear. So take the screenshot. Okay. Now we will go to the next part of this question. First part answered. A part clear. magnetic flux versus time and alternating EMF versus time. Okay, so magnetic flux versus time graph, okay, because it is cos omega t, okay, phi, and E is d phi by dt, so sin omega t. So sin theta starts with 0, sin 0 is 0, and cos theta, cos starts with cos 0 is equal to 1 plus 1, correct? So this is the difference between phi and EMF induced, correct? Now, in fluorescent lamp circuit, choke limits current. Okay, there is a choke coil we normally use in earlier model tube light. We have a choke coil, okay, and prevents the lamp from creating a type of short circuit which would destroy the lamp. Choke coil provides high voltage pulse required for starting of the lamp. Thus, it reduces voltage across the fluorescent tube without wasting power. So this is the use of choke coil. This question was asked here. Why a choke coil is used? Okay. So this is in the fluorescent tubes like tube light with AC mains. So choke coil. I have not gone to because simply 1 mark question. How much is the mark carrying? Half marks question. So this much answer is sufficient to fetch 1 mark, half marks. Now, what are permanent magnets? I give one reason. Permanent magnets are which has the higher retentivity, means on applying the magnetization external field, it develops a permanent magnetism. Okay, even after withdrawal of the external magnetic field, it retains its magnetism. Okay, so permanent magnet is made up of material which are magnetized and retains high retentivity, okay, for longer time. Okay, has high corrosivity and remanence of retentivity, or retentivity is more actually, it retains the magnetization. So magnetic moments of atoms gets aligned permanently in a way that resulting magnetic moments of all atoms gives persistent magnetic field even after removal of external magnetic field. Okay, so actually basic reason of magnetism, if I want to explain you, it is the electron which is moving in orbits, okay, in about their axis. Okay, so there are two movements, one is the spin movement, other is orbital movement. Okay, so if the electron moving means it is similar to a circular loop, current loop, correct? Charge moving in a loop is a current loop. Current loop means it is just like a magnetization. It will develop north pole, south pole, correct? So if the magnetic moments, because of this electron movement of valence electrons, if they are cancelling each other, then resultant thing is 0. But if after external magnetic field, it impacts all these things, and their domains gets aligned with the external magnetic field. Okay, so we will come to the modern physics when we will go to in that level. Then we will explain what is the reason for magnetism. But for the time being, your examination is knocking your door, so this much is sufficient. So give one example. Okay, so example of permanent magnet is alloys of aluminium, nickel and cobalt, Al-Nico. Okay, Lenge's law. What is Lenge's law? A metallic rod. Okay, and what is straight Lenge's law? Lenge's law is what? The direction of induced EMF is such that so as to oppose the very cause due to which it is produced. So it is very philosophical statement. Okay, Lenge's law is such that the reason for which it is produced, okay, the direction of induced will be such that it will oppose the reason, it will oppose the cause, correct? If north pole is approaching, then north pole will be developed so that it can repel. Okay, so it gives direction of current and induced EMF in the circuit. Now, a metallic rod held horizontally along east-west direction is allowed to fall under gravity. Will there be EMF induced at its ends? Okay, so if metallic rod is there, it is falling under gravity, but there is a terrestrial magnetism involved. Okay, terrestrial magnetism, earth is a magnet. Okay, now if earth is a magnet, suppose, So it has a magnetic north and magnetic south. Okay, so a falling bar, a falling iron article, or a falling metallic rod is crossing this magnetic field. So magnetic lines of force will vary, EMF will be induced, correct? So we know the source is a magnetic field, north-south direction. Here velocity of the rod is along the downward direction, so magnetic field is cutting the plane of the metallic rod. Hence, because of this, electromagnetic induction will happen and EMF will be induced across the rod, correct? So this is the reason. Now an EM wave is traveling in a medium with velocity V equal to electromagnetic wave. So this will explain in the later chapter. Let me see. Okay, so it's a simple question. Okay, so this is electromagnetic wave is traveling in a medium V equal to Vi. Draw the sketch showing that the propagation of electromagnetic wave, okay, propagation of electromagnetic, suppose E and electric vector and magnetic vector is perpendicular to each other, and propagation vector K is perpendicular to the plane of E and B, correct? This is how electromagnetic wave moves. So indicating direction of oscillating electric and magnetic fields. Okay, how the magnitude of electric and magnetic fields related to velocity of the electromagnetic wave. Okay, let us see. So this is not related to electromagnetic induction, but it is related to the next chapter. Okay, but since questions is here written, so I'll explain it. So this is the electric field, this is the magnetic field, they are mutually perpendicular, and propagation vector K is along the perpendicular to this. So if orthogonal system of axis is taken, x, y, this is x, this is y, and perpendicular to x and y is z, correct? So this is how the electric magnetic vector vibrates. So when, okay, now second part, the velocity of the electromagnetic wave is ratio of magnitude of electric vector to the magnitude of induction vector, means magnetic field. Okay, so E by B, this is the velocity, this is how it is moving. Okay, next question. So you can take the screenshot. Just how many more questions are there? Let me check, because this needs to be cleared today. No, it needs one more class to explain. Okay, so we will end up here because this video is too long now. So we will take up our next class. We will finish it in our next class. Thank you very much.